Building airtightness, also called envelope airtightness, can be defined as the resistance to inward or outward air leakage through unintentional leakage points or areas in the building envelope. This air leakage is driven by differential pressures across the building envelope due to the combined effects of stack, external wind, and mechanical ventilation systems. Airtightness is the fundamental building property that impacts infiltration, the uncontrolled inward leakage of outdoor air through cracks, interstices or other unintentional openings of a building, caused by pressure effects of the wind and/or stack effect. An airtight building has several positive impacts when combined with an appropriate ventilation system, whether natural, mechanical, or hybrid. Lower heating bills due to less heat loss, with potentially smaller requirements for heating and cooling equipment capacities. Better performing ventilation system, reduced chance of mold and rot because moisture is less likely to enter and become trapped in cavities. Fewer drafts and thus increased thermal comfort. A number of studies have shown substantial energy savings by tightening building envelopes. Experimental data showing the energy savings of good airtightness were also published by the Building Research Establishment in the UK as well as Revit Journal's special issue on airtightness. Given its impacts on heat losses, good building airtightness may allow installation of smaller heating and cooling capacities. Conversely, poor airtightness may prevent achieving the desired indoor temperature conditions if the equipment has not been sized with proper estimates of infiltration heat losses. From an energy point of view, it is almost always desirable to increase airtightness, but if infiltration is providing useful dilution of indoor contaminants, indoor air quality may suffer. However, it is often unclear how useful this dilution is because building leaks cause uncontrolled airflows and potentially poorly ventilated rooms, although the total building air exchange rate may be sufficient. This adverse effect has been confirmed by numerical simulations in the French context, which has shown that typical mechanical ventilation systems yielded better indoor air quality with tighter envelopes. Air leaking out of the envelope may cause condensation damage as its temperature drops below dew point.